Hello all. So in today's class we will see a few basic theorems concerning about linearly independent solutions. Then we will look at a basic theorem on what is a general solution of a homogeneous linear system, and then we will look into what is the general solution of a non-homogeneous linear system. Okay. So നമ്മൾ ഡിഫറൻഷ്യൽ ഇക്വേഷനകത്ത് കുറേ ബേസിക് തിയറംസ് കണ്ടിട്ടുണ്ട്. സേ ഫോർ എക്സാമ്പിൾ, ഇഫ് യു ഹാവ് a differential equation of the form a naught x y double dash, and taking a second order equation a1x y dash plus a2 of x y equal to 0. So this is second order equation, second order homogeneous equation. So if you have two linearly independent solutions, so if y1 and y2 are two linearly independent solutions of this equation, then their linear combination c1 y1 plus c2 y2, that will be called the general solution of this equation. Now the solutions y1 and y2, they will be linearly independent provided when you take the Wronskian. So Wronskian is given by determinant y1 y2 y1 dash y2 dash. So if this determinant is not equal to 0 for some t belongs to the interval a b, so then the solutions are linearly independent, and if this is identically equal to 0, the solutions are linearly dependent. So that is one way of finding out whether the solutions are linearly independent or dependent. പിന്നെ നമ്മൾ കണ്ട എങ്ങനെ c1 y1 plus c2 y2 equal to 0 implies if both c1 and c2 both are 0, they are linearly independent, and if at least one of them is not 0, they will be linearly dependent. Okay, and again if you have a non-homogeneous equation, so if you have a right hand side function f of x here, then the general solution will be of the form yc plus yp. In yc nu parayna, that is a general solution of the associated homogeneous equation, and yp is the particular solution. So that is any solution which satisfies the non-homogeneous equation. So this is the form of this is a form of general solution of a homogeneous equation, and for a non-homogeneous equation this will be the form of the solution. In second order equation anengil, the general solution will contain exactly two arbitrary constants. So these are the few results. You can generalize this to a differential equation of nth order. The same thing applies. Okay, so we will see the analogous results similar to this. So results similar to this for the linear system, for the homogeneous linear system, and then we'll move on to the non-homogeneous linear system. So okay, so the first theorem we'll be seeing is what is going to be the general solution. So first of all, we look into what is the general solution of a homogeneous linear system. So we will have two theorems. Okay. First we have a theorem. So the theorem states that there exist sets of two linearly independent solutions of the homogeneous linear system and every solution of the system can be written as a linear combination of any two linearly independent solutions. So if you have a system of the form dx by dt equal to a11 of x, sorry, a11 of t varum, so a11 of tx plus a12 of t y, and if you have dy by dt equal to a21 t of x plus a22 t of y. So the theorem states that there exist sets of two linearly independent solutions of the homogeneous system. So there will be two set of solutions. So you will have the pair f1 g1 and the pair f2 g2. So for any linear system there will always exist two linearly independent solutions, and every solution of the system will be a linear combination of any two independent solutions. So every solution is going to be of the form, so x of t will be of the form c1f1 plus c2f2, അതുപോലെ y of t will be of the form c1 g1 plus c2 g2. So that will be the form of the solution. So with this we define now the general solution of a linear homogeneous system. So we will give the definition of general solution. So we must have two pairs of independent solutions. So let me take, so let x equal to f1 of t, y equal to g1 of t, and x equal to f2 of t and y equal to g2 of t be two linearly independent solutions of the homogeneous linear system. So I'm not mentioning the homogeneous system. So this is the homogeneous system. We are talking about dx by dt equal to a11x plus a12y and dy by dt equal to a21x plus a22y. Okay. So you are having the pairs f1 g1 and f2 g2, and they are two linearly independent solutions of the homogeneous linear system. Then the solution x equal to c1 f1 of t plus c2 f2 of t and y equal to c1 g1 of t plus c2 g2 of t is called the general solution of the system. So this is called the general solution of the homogeneous system. So those are the two. So first we have seen a theorem regarding the solution. So for every homogeneous system you will always have a pair of linearly independent solutions. So there will exist a set of two linearly independent solutions. So you will have solutions f1 g1 and f2 g2, and every solution is going to be a linear combination of any two linearly independent solutions. So the general solution of a linear homogeneous system will be of the form x equal to c1 f1 plus c2 f2 and y equal to c1 g1 plus c2 g2. And now we will now look into another definition for linear independence and linear dependence using Wronskian. So here Wronskian is calculated in a different way. Okay. So for linear system, we will look at how to find the Wronskian. So let us again take the solutions f1 g1 and f2 g2. So let x equal to f1 of t, y equal to g1 of t, and x equal to f2 of t, y equal to g2 of t. The two solutions of the homogeneous linear system. Now the determinant, so f1 of t, f2 of t, then g1 of t, g2 of t is called the Wronskian. So we will denote it by, and it's denoted by, so this is going to be a function of t, so that will be denoted by w of t. So നമ്മൾ linear independence linear dependence check ചെയ്യുന്നത്, so if c1 f1 plus c2 f2 equal to 0, and if you have c1 g1 plus c2 g2 equal to 0, so if both c1 and c2 are 0, you will get a linearly independent solution, and if one of them is not 0, then in that case it is linearly dependent. But this can be put in the form of a matrix. So f1 f2 g1 g2, then you will have c1 c2 equal to 0. So this is a homogeneous system of equation. In a, this will have a non-zero solution when determinant of f1 f2 and g1 g2. So if this is non-zero, then the only solution is going to be c1 c2 equal to 0. So for c1 c2 to be equal to 0, this determinant has to be non-zero. So when the Wronskian is non-zero, that gives us linearly independent solution, and this will have a non-zero solution when the determinant is actually equal to 0. So that comes by the property of matrices. So this will give us the condition for linear independence and dependence using the Wronskian. So we will write that as a theorem. Okay. So that gives the next theorem. So two solutions. So x equal to f1 of t, y equal to g1 of t, and x equal to f2 of t, y equal to g2 of t of homogeneous linear system, of a homogeneous linear system are linearly independent on an interval a less than or equal to t less than or equal to b, if and only if the Wronskian is is different from 0. For all t belongs to the closed interval AB. So that gives the condition for linearly independent solution. So the Wronskian must be different from 0. So in that case, the solutions will be linearly independent. And we have one more theorem on the behavior of Wronskian. So let Wt be the Wronskian of two solutions of the homogeneous linear system on interval a less than or equal to t less than or equal to b, then either w of t will be equal to 0 for all t belongs to closed interval ab, or w of t will be equal to 0 for no t belongs to closed interval AB. So that is a property of the Wronskian. So if the Wronskian is equal to 0, so it will be identically equal to 0 for all t belongs to an interval, and if it is not 0, it will be not equal to 0 for all t in a given interval AB. So, if Wronskian is not equal to 0, the solution will be linearly independent, and when the solutions are linearly dependent, the Wronskian will be identically equal to 0. So, let us see an example of finding the Wronskian. So, if you have the solution, say x equal to e raised to 5t and y equal to minus 3 e raised to 5t, and if you have x equal to e raised to 3t, y equal to minus e raised to 3t. So this is the pair, first pair f1 g1, and this is f2 g2. So w will be determinant. So you will have f1 f2, so e raised to 5t varum, e raised to 3t varum, then minus 3 e raised to 5t and minus e raised to 3t. So that is minus e raised to 8t plus 3 e raised to 8t. So that gives 2 e raised to 8t. So this is not equal to 0. So therefore the solutions are linearly independent. So this is how check the linear independence and dependence for the pair of solutions. And okay, so with that we will conclude for today's class. So next class we will look at the solution of a non-homogeneous equation.